Hi guys, so we're ready to finish up work on 6.5 trigonometric equations. So the very first thing I have here is just kind of reviewing domain and range of each trig function. But I wish I would have added to this table. I also want to just review the period really quick as well, right? So if you would, just go ahead and add that off to the side, and we'll review those. But this is some information that you should already know, but just to kind of refresh ourselves, because we're going to need it in this section. It's going to come up, right? So the domain for cosine of x is all real numbers, right? So negative infinity to infinity. The range is negative 1 to 1 inclusive. And the period is 2 pi, right? So then for sine of x, it's exactly the same actually, right? It's negative infinity to infinity for the domain, negative 1 to 1 inclusive, and the period again is 2 pi, right? So tangent, the domain, so remember tangent's undefined for all odd multiples of pi over 2, right? So how that looks is the domain is any x such that x is not equal to 2n plus 1 times pi over 2, right? And in this case, in this table, I'm going to let n be an integer, right? So n is within the set of integers, right? So you can use that notation, or if you're more comfortable, we can just say n is an integer, right? So then the range of tangent is all real numbers. And the period, though, remember the period of tangent is pi, right? And then for secant, the domain for secant is actually the same for tangent, right? So that's any x such that x is not equal to 2n plus 1 times pi over 2, right? Again, we can't have odd multiples of pi over 2. And then for secant, the range is any y such that y is less than or equal to negative 1, or y greater than or equal to 1, right? Positive 1. And the period for that is 2 pi. And then cosecant, we can't have multiples of pi in this case, right? So we would have any x such that x is not equal to n times pi. And the range is the same for secant, right? So that would be the set of any y such that y is less than or equal to negative 1, or y is greater than or equal to 1. And the period for cosecant is 2 pi. Right? Then lastly, cotangent. The domain is the same as cosecant, right? It's any x such that x is not equal to a multiple of pi. And then the range for cotangent is negative infinity to infinity. Right? And then the period is pi. Right. So again, that's just to refresh ourselves a little bit on domain, range, and period of the trig functions, right? So what we're working on here is trying to solve trigonometric equations, right? So objective 1 is being able to solve trigonometric equations in linear forms. These are going to be the most, maybe the easiest examples, right? So first of all, what I have here is just a motivating example. It says to solve the equation for cosine of x equals a half, right? So if we kind of think about this on the unit circle a little bit, right? Remember, cosine of x equals a half. If x is my angle, remember the cosine value is the x-coordinate, right? So, here would be an x-coordinate of 1, right? And then somewhere in the middle is going to be a half. And then if I go straight up, we're going to get a point here. And if I go straight down, we're going to get another point. So I actually have two points that have an x-coordinate of a half, right? So this point would actually be 1/2 comma radical 3 over 2. And this point would be 1/2 comma negative radical 3 over 2, right? So this is actually from the unit circle, right, where this angle here is pi over 3, right? And then this angle all the way over here, that's what, 5 pi over 3, right? So this is just from the unit circle, right? Just pulling out those points, right? So when we're thinking about this, you know, it's possible that maybe we just restrict x to be within the interval 0 to 2 pi, right? So in other words, like one rotation. If that's the case, those are the only two solutions that are going to exist, right? X would be equal to pi over 3 or 5 pi over 3, right? But you could imagine, though, if we think about like a general solution, if I have this angle here and I go around like a full rotation and still land at pi over 3, right? So in other words, 2 pi plus pi over 3, I'm going to land at that spot again, right? And then I could do, another multiple of 2 pi. So maybe I go 2 full rotations and add 2 pi to that. So you could imagine that there's really an infinite number of possible solutions, right? So what we mean by the general solution, we could say the general solution is, and we need a set for this, x equals the set of any x such that x equals pi over 3 plus 2n pi, right? So multiples of 2 pi, or x could be equal to 5 pi over 3 plus 2n pi, right? Where n is an integer, right? So in other words, there's an infinite number of solutions, right, in the general solution, right? If we're bounded in just one full rotation, right, like here that I put in the box, then there's only two solutions, right? But if we're not restricted the domain at all, then there's an infinite number of solutions. And if we look on the next page, I actually have a printout from Desmos that shows this graph, right? So what we're trying to solve for is when is cosine of x equal to a half, right? So what I did is I graphed in y1, I put cosine of x, and then in y2, I put 1/2, right? So this blue line, right, is y equals a half, and this red line is cosine of x. So you can see at the points where they intersect, these are going to be solutions then for that equation, right? It's just another way of finding those. So you can see what we found was pi over 3 and 5 pi over 3, right? So there's 5 pi over 3 and there's pi over 3. So if we're stuck in between 0 and 2 pi, right, in between here, you can see that those are the only two possible solutions, right? But then if I'm at pi over 3 and I add 2 pi to this, right, then I get another solution here, right? Same if I were to subtract pi, right? If I subtracted pi, then I'd be over here, right? So we get another solution. And similarly, if I take this solution at 5 pi over 3 and subtract pi, or subtract 2 pi, rather, then I get over here at negative pi over 3, right? So you can see we get these, if we add 2 pi, add the period to it, it's just going to keep repeating, right? Because that's what we know about cosine, is it has a period of 2 pi, so every 2 pi is just going to keep repeating itself, right? So those are just some things that we have to keep in mind when solving these equations, right? It's maybe a little different, more involved than just solving an equation for x, right? So then, example 1, we want to solve sine of x equals radical 2 minus sine x, right? So here, I'm thinking, let's see if it's possible for me just to get sine x by itself, right? So if I start with sine x equals radical 2 minus sine x, then I could add sine x to both sides. Right, so that gets me 2 sine x equals radical 2. And then I can divide both sides by 2, and I end up with sine of x equals radical 2 over 2. Right? So we can think about for a moment, like our basic triangles, is there, an angle in one of our special right triangles that has radical 2 over 2 for sine, right? And there is, right? So if we have, right triangle with pi over 4 as my angles, right, then this is 1 and this is radical 2 over 2, right, for the legs. Right? So looking at this, though, notice that this is positive radical 2 over 2. Right? So if I think about the sine, all students take calculus, sine is going to be positive in the first quadrant and the second quadrant. Right? So I know that sine of pi over 4 equals radical 2 over 2. So that's going to be my reference angle, right? So here to here, that's going to be pi over 4. This angle is also going to be pi over 4, right? So my solutions that I want here, so if I have the set of x's, right, I know pi over 4 is going to be in here. And then this guy is going to be this angle here, right? We're also going to have that angle as a solution, this one. So how do I find that? Well, that angle is pi, right? Because this, if I go all the way over here, that's pi. Then I need to subtract pi over 4, right, to land in this spot. So if I take pi minus pi over 4, I need to get common denominators, right? So this would be 4 pi over 4 is the same thing as pi. So 4 pi over 4 minus pi over 4, we get 3 pi over 4. Right, so that's the other point there, right? And we're limiting ourselves just between 0 and 2 pi, right? So those are the only possibilities. So then for part B, if we want over the whole set of real numbers, right, in other words, getting a general solution, right, that would be the set of any x such that, and then sine has a period of 2 pi, just like cosine did, right? So this would be anytime x equals x plus 4 plus 2n pi, or if x equals 3 pi over 4 plus a multiple of its period, 2n pi, where n is an integer. Right, so that would be the solution set over all the real numbers, right? Remember, we call this the general solution set. Right? So then, objective 2, we want to look at solving trig equations involving multiple or compound angles. So something that's going to play in here, and I have this example, is if we look at for solutions for cosine of x equals a half versus cosine of 4x equals a half, right? So notice the difference is that b value, right? So here it's 1 and here it's 4, right? So the periods for these are going to be different, right? Because if you remember from previous sections, the period for cosine is equal to 2 pi over b, right? Where b is that value that's being multiplied by x, right? There inside, right? So in this case, b is 1. In this case, b is 4, right? So the period for cosine of x equals a half, the period would just be 2 pi, right? Because you'd have 2 pi divided by 1. The cosine of 4x, though, the period is going to be 2 pi divided by 4, which is pi over 2, right? So we end up getting a different period for those. So for cosine of 4x versus cosine of x, that's going to smush the graph, right? Kind of like an accordion, it's going to smush the graph inward, right? In other words, the period's shorter, so we're going to it's going to repeat itself more frequently in the same, kind of like the same span of x values, right? So I have this shown in the graphs below, right? So this first graph, I put y1 equals cosine of x and y2 equals a half, right? And then in the second graph, I put y1 equals cosine of 4x, and y2 equals a half. And we can see where those, see where they intersect, right, where the solutions are, right? So if we're looking at just between 0 and 2 pi, right, that's what we were asked to do. Notice that there's just two solutions here, where this one would not be within 2 pi, right? So the bottom one, there's 1, 2, 3, 4, 5, 6, 7, 8 solutions, right? And notice the b value is 4 before, and 8 is 2 times 4, right? So the previous number of solutions times the b value. So in other words, we got a multiple of 4 times as many solutions by having cosine of 4x, right? So that's kind of interesting to think about that a little bit, right? So this is just this kind of little example, just trying to convince you how that period is going to impact the number of solutions to the trig equation, right? So that's what this statement is about, right? So it plays an important role there, right? So let's try and look at some of these. So I have example 2, so we're solving the equation 1 plus cosine of 3x equals 0. Write the solution set for the general solution. So with these, the basic idea is going to be to solve for the trig equation, right? So we have cosine of 3x, that's 1 plus, right? 1 plus cosine of 3x equals 0. So if we solve for the trig function, if I subtract 1 from both sides, I get cosine of 3x equals -1, right? But trying to solve for cosine of 3x is maybe a little difficult. So what we can use is what's called u substitution. So I can just say let u equal 3x, right? And that would give me cosine of u equals -1. Right, so that just makes it a little easier to solve now, right? Because I just have cosine of a variable equals -1. Well, we can kind of think through and figure out what that solution would look like, right? So if I just draw like the unit circle, remember the cosine value is the x-coordinate, right? So this point here is the point -1, 0. So that point, that angle is going to be the solution. Well, that's pi, right? So in other words, what we know is that u is going to be equal to pi, right? But here we're doing the general solution, right? So the period for cosine is 2 pi. So actually, if I take and add a multiple of 2 pi, or 2n pi, then that's going to produce another solution, right? We're just adding in more rotations, right? So we would have the same terminal side, right, for that angle, right? So since u equals pi plus 2n pi, I mean, really what we're trying to find, we're trying to solve for x, right? That's the variable I'm trying to solve for. So what I can do is substitute this value back in for u. So that gives me 3x equals pi plus 2n pi. And then I can solve for x, right? So in order to solve for x, I'm going to have to multiply or divide both sides by 3. So this gives me that x equals pi over 3 plus 2n pi over 3, right? Where again, n is just some integer, right? So the general solution is the set of any x such that x equals pi over 3 plus 2n pi over 3, where n is an integer. Right? So there's the general solution. Right? So then the next part, what we're asked to do is write the solution set on the interval 0 to 2 pi, right? And basically the way to think about it is, since we have this general solution here, just plugging in different values of n, and I want to be, I only want to look for the angles that are inside of this this interval, right? So the way I like to approach it, and the way the textbook approaches it, is through doing a table, right? So in other words, we're going to plug various n values in, and then my general solution is x equals pi over 3 plus, so really we could rewrite that as 2 times n times pi over 3. Right, that's the same thing as this term. So that'll make it just a little bit easier to work with, I think. And then the next column, we basically just want to ask ourselves, is this in the interval 0 to 2 pi, right, in the interval that we're wondering. Right, so I'm going to plug n values of -1, 0, 1, 2, and 3 into this. Right? Basically, the idea that you want to do is find an n value that doesn't work, and then once you find one that does work, you keep going until you find another n value that no longer works, right? So if I plug -1 in, we would have x equals pi over 3 plus 2 times -1 times pi over 3. So this would be pi over 3 minus 2 pi over 3, which is equal to negative pi over 3. Right, so this is not in that interval, right? That's too big, or too small, right? It's less than 0. So then if I plug 0 in, that would be pi over 3 plus 2 times 0 times pi over 3, which this whole second term is just 0, right? Because there's a factor of 0. So this just would become pi over 3 plus 0, which is just pi over 3. Right, so this is in the interval that we're looking for. Right, pi over 3 is inside of here. Right, so if I plug 1 in, that would be pi over 3 plus 2 times 1 times pi over 3, which gives me pi over 3 plus 2 pi over 3, which is 3 pi over 3, right, which is just pi. Right, so yes, that's also in that range, right? And then if I plug 2 in, this would give me x equals pi over 3 plus 2 times 2 times pi over 3, which that gives me pi over 3 plus, that'd be what, 4 pi over 3, which equals 5 pi over 3. So that's less than 2 pi, right? Because 2 pi would be equal to 6 pi over 3, right? If I want a denominator of 3. So that's less than 6 pi over 3, right? So that would still be good. And then if I plug 3 into this, we get x equals pi over 3 plus 2 times 3 times pi over 3, which gives me pi over 3 plus, and then that would be, what, 6 pi over 3, which gives me 7 pi over 3. But that's going to be bigger. This is bigger than 2 pi, right? So this is a no. It's not in that interval, right? So then basically what we found is that my possibilities of x between 0 and 2 pi is pi over 3, pi, and 5 pi over 3. Right, those are the only ones that work. Right? So then example 3, we're trying to solve the equation 1 plus 2 cosine of x divided by 2 equals 0. So again, with this one, you know, it's easy enough just to get the trig function by itself, right? So if at all possible, then you want to do that. So this would be 1 plus 2 cosine of x divided by 2 equals 0. So if I would solve for cosine, you know, I'd want to subtract 1 from both sides first. So we get 2 cosine of x divided by 2 equals -1. And then divide both sides by 2. We get cosine of x divided by 2 equals -1/2. Right? So thinking about this, right, I do have a special right triangle that's going to have 1/2 as a possibility, right? So, you know, we'd have, if this is pi over 3 and this is pi over 6, right, this would be, 1 and then 1/2 here, and then 3 halves, or excuse me, radical 3 over 2, right? So then, if I want cosine to equal negative a half, right? Cosine would be the adjacent, right? So that would deal with the angle pi over 3, right? So if I let u equal x over 2, then what we'd be solving for is when is cosine of u equal to negative 1/2, right? So if I draw, my xy system, right? All students take calculus. Then cosine, right? This is negative, so it's going to be negative in the second quadrant and the third quadrant, right? So as we mentioned before, I know that reference angle is going to be pi over 3, right? Because cosine of x equals 1/2, right? Oops, cosine of pi over 3 is what equals a half, right? So that reference angle is going to be pi over 3. Right? So then to find those angles, right, we would have, u equals pi minus pi over 3, or u equals pi plus pi over 3. Right, so we would subtract to get the first one, this one, and then add pi over 3 to get this angle. So this would be the same thing as 3 pi over 3 minus pi over 3, which gives me 2 pi over 3. And then here this would be equal to 3 pi over 3 plus pi over 3, which equals 4 pi over 3. Right, that's a 3 here, 3 pi. Right? So in other words, u equals 2 pi over 3, or u equals 4 pi over 3. So the general solution for u, right, since we're dealing with cosine, we would have to add 2n pi, right, because the period's 2 pi. So in general, we would have u equals 2 pi over 3 plus 2n pi, or u is going to be equal to 4 pi over 3 plus 2n pi, right? But again, we're not trying to solve for u here. We're just kind of a middleman. We want to solve for x. So now's the time where I'm going to use this fact to plug x divided by 2 in for u, so I introduce an x variable again. So we'd have x divided by 2 equals 2 pi over 3 plus 2n pi, or x divided by 2 equals 4 pi over 3 plus 2n pi. Right? So now what I want to do is multiply both sides by 2. Right, and really both equations. That way I can get x by itself. So this would give me x equals 4 pi over 3 plus 4n pi, right? Or x would be equal to 8 pi over 3 plus 4n pi. Right? So then the general solution would be any x such that x equals 4 pi over 3 plus 4n pi. Oops. Make that 3 a little better, right? Or x equals 8 pi over 3 plus 4n pi, where n is an integer. Right? So that would be the general solution, what we were asked to find. So then, now what we're trying to find is, right, the solution set on the interval 0 to 2 pi, right? So we want to be restricted just between 0 and 2 pi. So again, I like to approach this with a table, right? Just plugging in various values for n and seeing what works in that interval. The difference here between this one and the last one is that we actually have 2 different general equations, right, for x. So x can be 4 pi over 3 plus 4n pi. And then x would be equal to 8 pi over 3 plus 4n pi. Right? So if I plug in n of -1, I can plug in n of 0 and maybe 1. That's actually going to give us all the solutions we need, right? So like in the first one, if I plug -1 in, I get 4 pi over 3 plus -4 pi, which is just equal to 4 pi over 3 minus 12 pi over 3, right? So getting a common denominator of 3, that gives me -8 pi over 3, right? So that one doesn't work. That's less than 0, right? And then if I plug in 0 into this, right, we would get x equals 4 pi over 3 plus 0 equals, that would be 4 pi over 3, right, plugging in 0 in value of 0. And then the next one, if I plug in 1, we get x equals 4 pi over 3 plus 4 times 1 times pi. That gives me 4 pi over 3 plus, and we get common denominator, that'd be 12 pi over 3, which this gives me 16 pi over 3, right? And that's too big, right? Because 2 pi would equal 6 pi over 3, right? To have a denominator of 3. So that's definitely bigger, right? So right now, the only one that worked was 4 pi over 3. Right? So then now if we work with the second general equation, if I plug -1 in, that would give me x equals 8 pi over 3 plus 4 times -1 times pi, which equals 8 pi over 3 minus 12 pi over 3 equals -4 pi over 3. Right, so that one doesn't work, right? That's less than 0. If I plug 0 in, that would be x equals 8 pi over 3 plus 4 times 0 pi. Oops. Which is just equal to 8 pi over 3, right? Because this part is just 0. And that's too big, right? So this one was less than 0. This one's too big. So if you imagine if I add any more positive multiples of 4 pi, this number is just going to be, too big. So in this column, there's actually no solutions in between 0 and 2 pi, right? So this one doesn't generate any. So actually the only solution between 0 and 2 pi is this one, right? So the solution set would just be 4 pi over 3, right? That's the only value for x that makes that equation true, right? In between 0 and 2 pi. All right. All right, so now ready for example 4. So we have the cotangent of x minus pi over 4 equals -1, right? So this one we don't have to really do a lot to it, right? It's already solved for a trig equation, right? I have cotangent of something equals -1. So the very first thing I would do is, let u equal the inside, x minus pi over 4, right? So what that gives me is that cotangent of u equals -1, right? So that makes that a little easier to work with, right? And remember, if cotangent of u equals -1, then tangent of u would equal the reciprocal, right? But the reciprocal of -1 is just -1, so tangent of u would equal -1, right? So putting in terms of tangent just is easier for me to work with, right? Because we like to, it's nice to think of things in terms of sine, cosine, and tangent. So then, when is tangent of u equal to -1, right? So if we think about, when is tangent equal to 1 or -1, so forth, tangent is going to equal 1 when this y and x values are the same, right? So in other words, when you have a pi over 4, 45, 45, 90-degree angle, right? So this is 1, this is radical 2 over 2, right? And this is radical 2 over 2. So then when I take this side divided by this side, that's how I get 1, right? So tangent is negative, right? All students take calculus. So tangent is going to be negative in the second quadrant and the fourth quadrant. So the reference angle is pi over 4, right, for both of these. Right? So then to find those, right, u would be equal to pi minus pi over 4, right? That's going to generate this guy, right, in the second quadrant. And then u would equal 2 pi minus pi over 4, right? That would give me this this one here, right? So this would equal, so if I get common denominators, that would be 4 pi over 4 minus pi over 4, which gives me 3 pi over 4, right? And then here, if I get a common denominator, 2 pi would be 8 pi over 4, right, minus pi over 4, which equals 7 pi over 4. Right? Something you want to notice is that if I take the first one, 3 pi over 4, and if I add pi to it, then we actually come up with 7 pi over 4. So in the period of tangent, like we talked about on the first page as a reminder, is pi, right? So really, I only need one of these, right? So in other words, if I just write down u equals 3 pi over 4 plus n pi, right, multiples of pi, that's going to give me all of the solutions in the second one, right? So that's really the only equation I need, right, where of course n is an integer, right? So then now if I plug this in for u, so now I can get it in terms of x, this would give me x minus pi over 4 equals 3 pi over 4 plus n pi. So I want to solve for x, so I can add pi over 4 to both sides. And I get x equals, so 3 pi over 4 plus pi over 4 would be 4 pi over 4 plus n pi. So 4 pi over 4 is just pi. So this gives me x equals pi plus n pi, right? So and really, thinking about more, since the period of tangent is pi, I don't really need this extra pi in here either, right? So in other words, this would be the same thing as if I just said x equals n pi, right? Just getting all of the multiples of pi, right? So in other words, the general solution set would just be any x such that x equals n pi. Right, so then part B, just like the others, we're trying to think about, well, what would the solution set be if we were stuck in the interval 0 to 2 pi? Right, so if I have n here and x equals n pi, and then the next column, is it n the interval 0 to 2 pi, question mark? We can figure that out. So we have -1, or you can plug that in, 0, 1, and 2. So if I plug in -1, that would be x equals -1 times pi, which of course is just negative pi, right? So that would be a no, right? It's not in there. This would be x equals 0 times pi, which is just 0, and that is in there, right? Because this is including 0. And then if I put in 1, that would be x equals 1 times pi, which is pi, which that's in there. And then lastly, I can multiply by 2, which gives me 2 pi, and that's not included, right? Because this parenthesis beside 2 pi means we're not including 2 pi, right? So this would be a no, right? So then the only answers for this would be 0 and pi, right? So x would equal the set 0 and pi, right? All right, so now we're going to start to solve maybe a little more difficult trig functions, equations. So objective 3, we want to solve higher degree trig equations. Objective 5, it says solve the equation on the interval 0 to 2 pi. Right, so that's important to note that we don't need the general solution. We just need to find all solutions between 0 and 2 pi. So here's my equation, my trig equation that I want to solve. So looking at this, I mean, this is like 2 times cosine of x quantity squared, right? That's what this means. Minus cosine of x minus 3 equals 0. Right, so this looks very much like a quadratic equation. Right, just like if I had 2x squared minus x minus 3 equals 0, right, from like college algebra. You know, some ways that we can solve this is that we can, you know, we could try factoring and apply the zero factor theorem, right? Which that just states, you know, if you have a times b equals 0, then a equals 0, or b equals 0, right? So in other words, if you have two things being multiplied together, their product is 0, then one of the factors must be equal to 0, right? That's the only way that could happen. So that's one method. And then the other method is you could use the quadratic formula. Right, and some of these, you know, the ones that we can't factor, we're going to want to use the quadratic formula. If you can factor, I mean, usually that is a little bit easier. But note the quadratic formula can, you know, can work for, you know, ones that can factor as well, right? So, you know, to be able to work with this and factor this, something that we might do is, you know, let u equal cosine of x, right? Because by doing that, we would have 2 u squared minus u minus 3 equals 0, right? So that looks a little easier to solve for and work with. So we can solve for u, and then we'll, you know, put it in terms of x and eventually solve for x, right? So it's just like a dummy variable almost, right? Just to kind of help us. So this one, you know, maybe isn't super easy to factor because there's not a 1 here, right? There's a 2 value there. So, you know, a common method that maybe you've seen before is called the AC method to factor, right? So this is in the form, you know, like ax squared plus bx plus c equals 0, right? So a here would be 2 and c would be negative 3, right? So what you do is you take a times c, so that would be 2 times negative 3, and we get negative 6, right? And then we want to denote the b value, which is this middle term, right, which is negative 1. So then what you want to think of are what are two numbers that are factors of negative 6 but have a sum of negative 1, right? So those numbers would be negative 3 and positive 2. So then what I'm going to do is rewrite this middle term, negative u, using those numbers, right, as the coefficients. So that would give me 2u squared. And it makes sense to maybe match the 2's together and the negative 3's together, right, in this case. So we'd have 2u squared plus 2u minus 3u minus 3 equals 0. So I just replaced, I just noted that negative u equals 2u minus 3u, right? So I took this and put it in place of this term. And then now I'm factoring by grouping, right? So I can group those together, and then I can pull out of 2u out of the first pairing, so that would be u plus 1. And then here I could pull out a negative 3, right? That would be u plus 1 equals 0. So then there's a common factor of u plus 1, so I can pull that out front. And then you multiply by what's left, which is 2u minus 3, and then this equals 0, right? So now I have it in this form for this to apply the zero factor theorem, right? So now what I know is that u plus 1 has to equal 0, or 2u minus 3 has to equal 0. So now I just want to solve for u, so I could subtract 1 from both sides here and get u equals -1. Or if I add 3 to both sides, I get 2u equals 3. And then divide both sides by 2, I get u equals 3/2. Right? So in other words, u is going to equal -1, or u is going to be equal to 3/2. Right? So now if I remember, what u was, right? U is equal to the cosine of x. So this would give me cosine of x equals -1, or cosine of x equals 3/2. Right? So just substituting what we had in for u back in, so now I can solve in terms of x. But notice that if you remember, cosine of x is going to be in between -1 and 1, right? That's the range for cosine. So 3/2 is bigger than 1. It's not in this range. So this is going to have no solutions, right? This is going to be what we call extraneous, right? They're extra. They don't work, right? But cosine of x equals -1. We can work with that. So this actually indicates that x would have to be pi, right? So I think we did this one previously today, but we're looking for this point, right, to have an x-coordinate of -1. So that, of course, goes with pi, right? So then the solution set would just be, x would equal pi, right? So that's the only solution for this one. Right. All right, so example 6, we have another one here. We want to solve the equation on the interval 0 to 2 pi again, but we have 4 cosine squared of x minus 3 equals 0. So notice that, I could solve this. This is kind of like, thinking about this as like 4u squared minus 3 equals 0. Like if I had asked you to solve something like this, you would probably just add 3 to both sides, divide by 4, and then take the square root, right, to get u by itself. There's no real need to factor anything there. So same idea, right? So what I can do is just start with 4 cosine squared x minus 3 equals 0, and I can kind of solve this like the linear ones, right? I can add 3 to both sides. 4 cosine squared x equals 3. Then I can divide both sides by 4 and get cosine squared x equals 3/4. And then I could take the square root of both sides, but remember we have to put a plus or minus on one of the sides since it's an even index, right? So that would give me cosine of x equals plus or minus radical 3/4. But radical 3/4, right, is the same thing as radical 3 over radical 4. And radical 3 doesn't simplify, but radical 4 is just 2. Right, so what we end up with is that cosine of x is equal to plus or minus radical 3 over 2. Right? So you just want to think about, what special right triangle has radical 3 over 2 in it, right? So that would be, this right triangle. So this is pi over 6, pi over 3. If the hypotenuse is 1, then the angle across from pi over 6 would be 1/2, and this would be radical 3 over 2. Right? So cosine is the adjacent angle, right? So my reference angle I want to get out of this is pi over 6. Right? So then if I draw an xy system, right? We're letting cosine be positive or negative radical 3 over 2. So that's going to generate, any quadrant, right? So I'm going to have all of these in different quadrants. And then my reference angles are going to be pi over 6. right? I want to find all 4 of those angles. Whoops. Sorry about that. Let me make this a little bigger, actually. Right? So I want to find all of those. So this first one is easy to find, right? That's just pi over 6. The second one here would be x would be equal to pi minus pi over 6, right? Which would equal 6 pi over 6, right? To get a common denominator, minus pi over 6, which is equal to 5 pi over 6, right? So that would be in here as a solution. And then to find the next angle, that would be equal to pi plus pi over 6, right? Because I'm at pi and I have to go pi over 6 more. So that would be 6 pi over 6 plus pi over 6, which is 7 pi over 6. And then this last angle, that would be found by taking 2 pi minus pi over 6. Right? So 2 pi with a denominator of 6 would be 12 pi over 6. So 12 pi over 6 minus pi over 6 equals 11 pi over 6. Right? So that's the last solution for that. Right? All right, so we're at right around 52 minutes. So I'm going to go ahead and end this video here, and I'm going to make a second part of this video to finish out these notes, because if I don't want to go too long, it gives some trouble to upload to YouTube. So I'll hang on, and I'll make a second video for finish out these section of notes.